And with that, I'd like to move to our final speaker of this session. So we next have a talk by Helen Q, who's a PhD candidate at the University of Pennsylvania. She will be presenting a talk entitled Photometric Supernova Classification in the Roman Era. I can see your slides there now. Thank you very much. And whenever you're ready.
Sorry, I can't see my mouse when I have the play button on. So is everyone able to hear and see my slides?
We can hear and see, and when you press play, we can now see the first slide that you have there.
Okay, perfect. Thanks so much. Yeah, thanks again to everyone for letting me present, and thanks to the organizers for really putting this together during such uncertain times. Like Rebecca said, my name is Helen, and I'm going to be talking about photometric supernova classification in the Roman era today. So first, we should ask why we care about photometric classification. And I guess the simple answer to that question is that in the when we lack spectroscopy, this is a really good alternative to be able to get some information about what we're looking at, right? And overall, I've sort of segmented the applications into two broad categories. The first is type 1a supernova cosmology, and the second is core collapse supernova astrophysics. So we'll go through each of these in turn. So for cosmology, we're primarily interested in procuring a pure type 1a sample, as a lot of the speakers today have already talked a lot in depth about. And we're also able to classify supernova events after they happen, which means that we are able to take advantage of all the information that a supernova gives us during its lifetime. For core collapse astrophysics, on the other hand, we primarily want to classify by supernova type. We just want to know, what we're looking at in the sky at any given moment. And we also want to be able to classify these events as early as possible because we want to be able to maximize our chances for follow-up observation to just get more information about these objects. So I'm just going to give a brief summary of each of these approaches, even though this has been said many times before. So type 1a supernova are ideal for cosmology because they're highly luminous, which means they're observable out to a redshift of 1 to 2. And they're also standardizable candles, which means that we can infer their distance from their brightness. And using the distance and redshift information, we're able to place it on a Hubble diagram, such as the one on the right side here. And we can use this Hubble diagram to infer the best fit cosmology parameters, such as these energy density parameters and the dark energy equation of state parameter W. And for core collapse astrophysics, we're primarily interested in understanding the progenitor physics of different supernova types. And the earlier we can get supernova type information, the more opportunities we have for follow-up observation. So in order to talk about what's different about our approach to photometric classification, we should talk about sort of what the state of the situation is at the moment. Again, this can be sort of separated into two broad categories, the first of which is template matching. This approach doesn't really have a lot of computational requirements, which is very good, but it sort of compromises a bit on accuracy. An example of this is PSNID. And the second group of approaches is machine learning based, which has higher computational requirements because they have, they require long training times, but rewards us in terms of giving us good accuracies. And an example here is a classifier called Supernova. So what we've developed is a classifier called SCONE, and it sort of bridges the gap between these two approaches in the sense that it doesn't really require a very long training time, and it also doesn't. It also has a good accuracy. So SCONE stands for Supernova Classification with a Convolutional Neural Network, and more details about the model and the results can be found in this paper that I linked on the bottom. And a convolutional neural network simply is just a deep learning framework that's specialized for image recognition. So I guess one natural question that comes out of that is what kinds of images are we using to train and evaluate this network? So the challenge here is to turn supernova photometry into images. On the very left side here, I've reproduced a 1 LSST supernova light curve in the UGRIS Y bands. And the first thing that we want to do is identify the active season that the supernova is actually in. So in this case, it's the first season that I've highlighted in green. And then once we take that portion of the light curve, we can perform a Gaussian process regression fit in the time dimension, which I've overplotted with these colored lines. You can also consider these light curves in wavelength and time space. So if you take each light curve and you map the light curve to the central wavelength of the filter that it's being imaged in, you can sort of make this three-dimensional plot where now flux is the z-axis and wavelength and time are the x and y-axes. And you can do another Gaussian process regression fit in the wavelength space, which gives you this smooth spectral surface that I've overplotted on top of the light curves in this middle panel here. And if you take this three-dimensional plot and you turn it on its head and you look at it from a top-down view, you sort of get this two-dimensional wavelength versus time projection that's colored by the flux values. And this sort of kind of looks like a picture or an image. And indeed, these are the images that we use to train our classifier. So here I've reproduced a few example images for different supernova types. Maybe these aren't necessarily representative of each type, but you can clearly see that even, as humans, we can tell that there's a lot of diversity going on within these images. And it sort of gives us some intuition that the differences, the things that help us differentiate between supernova types are sort of represented within these, like this type of image that we've chosen to use. So how well does this approach actually work? Now we can go back to our agenda and sort of look at the approaches one by one. So for cosmology, again, we're interested in a pure 1A sample and we can do classification after the fact. So this is a 1A versus non-1A classification problem, which means we're classifying between two classes. And this diagram that I've shown on the left is called a confusion matrix. It just shows the true positive and true negative rates on the main diagonal in red and the false positive and false negative rates on the off diagonal in blue. Mainly what we can see here is that the classifier isn't really biased towards any outcome because the two red numbers are quite similar, and the average is the accuracy, which is around 99.7%. And here we're doing classification without redshift information, which is a harder problem. And we've also gotten these results by training with 40,000 simulated supernova, which takes only about 15 minutes on a GPU. This is really orders of magnitude less time and fewer supernova than are needed to train other deep learning approaches in this space. So really a remarkable result. And an important caveat to note here is that these results are from simulated supernova data sets, and obviously real data is going to be messier. So now we can go on to talk about core collapse astrophysics, where we want to do typing, and we also want to do classification as early as we can during the course of the light curve. So in order to estimate, how well we can do on early time light curves, I've truncated existing data sets of light curves at different points during the lifetime. So here, I've started truncating at 0 days after trigger, where the trigger date is the second signal to noise greater than 5 detection on a different night than the first signal to noise greater than 5 detection. So starting on the left here, the plot shows accuracy as a function of the days after trigger. So right now we're looking at 0 days after trigger, which is the set of yellow points that I've highlighted. So it seems like we're doing about a 60% average accuracy. And on the right side, I've reproduced an image that was truncated at 0 days after trigger and the associated light curve and GP fit. So as we go on to 5 days after trigger, there are more observations, which gives the classifier more information. So the average, which is the pink dotted line, has gone up to almost 70%. And you can see that all of the colored lines, all the different supernova types are doing better in terms of classification accuracy. And as we go on to 15 days, 25 days, and 50 days after trigger, the classification accuracy continues to increase. So right now we're doing classification without redshift information, like I mentioned earlier. We found that if we add redshift information, which is this plot on the right, that increases the accuracy pretty significantly for all types across the board. As you can see, the color lines have moved up quite a bit between the left plot and the right plot.
3-minute warning.
Thanks. So just in summary, we are performing at about 60% accuracy, doing the 6-way typing on the night of trigger. And with the redshift information, we're able to get 75% accuracy. And by 5 days after trigger, those numbers increase to 70% accuracy without and 80% accuracy with redshift. So really quite good results considering we're doing classification between 6 different types here. So given that this is a Roman conference, we should talk about how well SCOAN performs on Roman data. So I've performed a simulation of Roman shallow and deep field photometry with a group of, with a realistic mixture of peculiar type 1a supernova and core collapse supernova as contaminants. As you can see on the plot on the right here, which is accuracy as a function of redshift. Again, the classification performs quite well. We're getting almost 99% average 1A classification efficiency, overall redshift bins with a 0.8% core collapse contamination. And the same caveat that I mentioned earlier applies where results on simulations may not translate exactly to real data, but considering that we're seeing pretty consistent classification accuracies between the LSST simulations I presented earlier and the Roman ones now, it really increases our confidence in the robustness of the classifier. So I've also performed some early time classification with Roman simulations as well, where we're doing, again, the 6-way photometric typing, and this time I've truncated it to 5 days after trigger. So based on the plot on the right, it seems like we're doing about a 70% average accuracy classifying without redshift, which is very similar to the result that we got from the LSST simulations that I presented a few slides ago. And you can see that there's kind of a counterintuitive increase in accuracy as a function of redshift. I believe that this can be explained by the plot on the bottom, which shows the number of objects from each type as a function of redshift. And you can see that after a redshift of 2 in the yellow box, that there are 2 lines that are way above everything else. So it seems like 2 supernova types are really dominating the population above redshift of 2, which just makes the classification problem a bit easier than when all of the types are in a more equal mix at lower redshifts. So in summary, today I've presented SCOAN, which is an image recognition based classifier that's quick to train. And I've shown that it's useful for cosmology in the sense that it's able to get more than 98% accuracy on LSST and Roman simulations. And it also has potential applications for core collapse astrophysics because it's able to perform the 6-way typing 0 or 5 days after trigger with pretty high accuracies, 60 to 80%. So thanks so much for your attention, and obviously happy to answer any questions.
Thank you very much, Helen, for that wonderful talk. Do we have any questions either on the Slack or via the chat for our speaker, please? Okay, I see that we have one question come up in the chat from Suvi Guraz to everybody. How many filters do you need to use this method?
That's a good question. So I've primarily been using LSST simulation. So there are 5 filters, 6 filters there. I have not checked whether, what percentage of, I guess one good test would be to see how the classification changes based on the survey strategy that we're using for Roman, and whether or not how many filters are available. But I haven't ever tried. I've also done DES simulations, so 4 filters, but I've never really tried with anything fewer than 4 filters. I don't know if there's really I'm sure there's some kind of minimum amount of information in wavelength space that you would need, but I haven't really tried to probe that minimum. So very good question.
Okay, thank you very much, Suvi. Do you have any other questions for our speaker? Oh, we do. So from Samaya, question for Helen: how was the data simulated? How were the supernova models chosen?
Yeah, so for the LSST simulations, it's actually part of a photometric classification challenge called Plastic. So I basically just took the same simulations that they did, and I just redid I use the same models, and I just like increased the like the number of simulations, or like changed a couple of other things. So I based it off of plastic, and for Roman, I based it off of some of Phil's simulations that he sort of presented earlier. Probably a better question for him.
Okay, any other questions for Helen or for any of our other speakers in this session? All right, if not, I'd like to take this opportunity once again to thank our speakers for their wonderful talks.